Hello and welcome to Team 4's final presentation for ISD 528. Here we will walk through our analysis and redesign of an electric conveyor oven. An electric conveyor oven is a piece of culinary equipment which enables continuous cooking of food by passing the food through a heated cavity on a wire belt. This product is primarily composed of metal, alloy, and polymer-based materials constructed from 20 to 30 different components. Estimated production volume is greater than 50,000 units. For this product, the primary customers are culinary professionals producing food for consumers and customers in cafes and restaurants, while the secondary customers are catering businesses, schools, universities, and hotels, which must produce food in abundance during peak periods in a given day. Here, an exploded view of the product is illustrated. This product includes 36 different types of parts with a wide variety of sizes.
To identify all our task functions, we created a fast diagram. The task function is to cook food and the primary basic functions are to heat and move food. We also focused on assuring dependability, convenience, enhancing product, and policing senses. This is our assembly sequence 1 shown in a fishbone diagram. There are 6 sub-assemblies: the base support, belt gear assembly, main body, motor assembly, switch panel, display panel. Then there are 3 individual components such as the unload tray, load tray, and heat shutter, which come together to form the conveyor oven. In our second assembly sequence, we still have 6 sub-assemblies, but the display panel and the switch panel are interchanged. And also we removed the top cover and the fan from the main body sub-assembly, and we put it towards the end of the assembly sequence.
We evaluated each assembly sequence against these criteria and concluded that sequence number 1 was more favorable. Our function component mapping matrix mapped each of our 18 terminal level functives with our 34 parts. This is our bill of material for the original design of our oven, with the original total product cost coming out to $932.14.
So regarding the function and component differentiation, both the customer groups require basic functionality. However, the secondary customer group would be provided functions such as illuminate food and guide food with the help of component modules such as light bulb, loading tray, and unloading tray. Based on the quad chart classification, parts such as the lower panels, heater mounting plate, side panels, top cover, fan, and heat shutter were categorized as eliminate. Parts such as bottom panel, collection tray, housing, loading tray, and unloading tray were categorized as redesign with DFMA, and rest of the components were categorized as keep as is.
Elaborating on product family design model comparison, both the offerings of the conveyor oven product are shown here. In product 2, new and redesigned components such as LED, loading, and unloading trays are assembled and demarcated to represent overall differences. Here you can see the interface of a loading and unloading tray with rail guides. Both the trays are attached to the rail guides using fasteners. In the overlapping image, you can see the dimensional differences between unloading tray 1 for the primary customer and unloading tray 2 for the secondary customers. Unloading tray 2 has been designed with the bigger dimensions to increase its capacity. Here again, you can see the dimensional differences between 2 loading trays. The loading tray 2 has been designed with the bigger dimensions and steep angle in order to increase its capacity and self-feeding feature. Differentiating products further, in the second image you can see for the secondary customers we have provided 2 LED lights, one on the each side of the loading tray and unloading tray. And for the base model we have just given a dummy plate in order to use the same top cover in both variants. These are 2 assembly diagrams with delay differentiation. In the second assembly diagram, the differentiation is done further down the line that results in saving in logistic and assembly costs as compared to assembly diagram 1.
For the selection of one assembly step for adding a platform part and a module part using design for manual assembly analysis, the total assembly time was found out to be 1235.48 seconds and the total assembly efficiency for manual assembly was found out to be 10.7%. The reason for choosing housing as a platform part and load tray as a module part was that both the parts were classified as redesigned with DFM in the quad chart classification with assembly times of 7.5 seconds and 8.5 seconds respectively. Also, with the aid of function component mapping matrix, it was analyzed that these parts would continue to support their designated functions even after redesign, leading to the overall decision.
The housing unit was redesigned for assembly. This included design changes such as including a bottom plate to increase stability and provide a locating feature for the collection tray, integrating the lower plate into the housing, adding additional ventilation holes, and adding a step to provide a locating feature for upper plate installation. The load tray was redesigned for assembly. This included modification of the mating component to support elimination of fasteners, replacement of the fasteners and hardware with insertable slot, and the addition of funneling plates to support food movement and improved ergonomics during installation.
This is our design for manual assembly analysis. The first table shows all the parts associated with before redesign, and the second table shows the after redesign. On the second table, you'll notice that there is no longer a right side lower panel, left side lower panel, bottom panel, and heat shutter. This is due to the change made for the housing. And then the load tray removed 8 bolts and nuts due to the insertable slot feature. This slide shows the comparison of before and after redesign. The redesigned part cut a total of 170 seconds from the assembly time. It is also 70 cents cheaper per build compared to the original design, and the assembly efficiency increased to 12.39%.
In design for automated assembly, we have selected switch panel and display panel subassembly. This selection was done based on function component mapping and chord chart. The chord chart was recommending to redesign these 2 blue color parts, that is switch panel and control module. After analysis of this subassembly for automation, we are getting 7 cents as a total assembly cost. Here you can see exploded view of before and after CAD. In the after CAD redesign, we have combined switch panel and control module. Along with combining switch panel and control module, we have reduced fastener counts from 8 to 6 and provided red color to power knob in order to differentiate it from other similarly shaped knobs. After redesigning parts for automated assembly, we reanalyzed the subassembly for automation, and we are getting 6 cents as a total assembly cost. Finally, the function analysis was carried out to see if we are impacting any functions. So we are impacting no functions, and we were able to save cost by about 1 cent.
We conducted process selection for a control module after redesign for automated assembly, with key dimensions shown here. Critical dimensions for the control module's function were thickness, length, and width. Ultimately, we recommended injection molding with polyethylene. We also conducted process selection for our housing after redesign for manual assembly. Critical dimensions for the housing's function were length and width. Ultimately, we recommended sheet metal working with stainless steel.
DFMPro was utilized to further analyze our product for additional refinement. It identified 3 potential concerns for the control module. However, it did not identify any concerns for the housing unit as currently designed. The control module was also redesigned for manufacturability. Design changes included modifying the wall thickness to improve the ability to injection mold the part, modifying the wall thickness to make it uniform across the component, and adding draft angles. Here we have the redesigned housing for manufacturability, which we increased the width of material on the edge of the component to improve structural integrity, increase distance between the holes for structural benefits, adjusted component radii to avoid sharp corners, and increase the distance between ventilation holes.
Due to the benefits of designing for manufacturing of our housing, there is a net decrease of 13 cents per part post redesigning for manufacturing, and that's due to the decrease in material cost.
Similarly, for the control module part manufactured using injection molding process, there is a net decrease of 17 cents per part by using design for manufacturing methodology.
This product has a service system which is focused around warranty, serviceability, and sustainability, and includes a 1-year product warranty for any potential part replacement covered due to potential defects.
The table below shows the comparison of analytical versus hubs. At first, in the before redesign, you can see hubs is calculating $108. That was due to the complexity and the geometry before redesign. And then after we did redesign, we were able to get the cost down to $47, which is within 10% of the value of our analytical method.
Here, a final product comparison is illustrated. The image on the right highlights 4 of the primary areas where redesign took place, including the redesigned control module, redesigned housing, and the redesigned load tray.
To conclude, the overall benefits gained through DFA and DFM are total cost reduction of $152.36, which is reduced by 16%. The number of parts are reduced by 25 numbers, which is effectively reduced by 14%. And the reduction in assembly and manufacturing time by 170 seconds, which is reduced by 13%. The pros are robust product design with improved assembly times and interfaces, whereas the cons are lack of product mobility with relatively higher product weight to size ratio. A major alternative approach could have been that the customer requirements could have been translated to functional requirements and then into product features using DMA-DV design approach with further component integration to reduce part count. Thank you for being a part of our presentation. Now our group would be happy to take up questions.